So, this brings us to a very interesting part of this chapter, which is around rockets. We all know that when a rocket spews out exhaust gases at high velocity, Newton's third law of motion dictates that the rocket should get propelled in the opposite direction because the law says that to every action there should be an equal and opposite reaction. But how does the law of conservation of linear momentum apply to a system of masses, and in this case, the rocket and the exhaust gases, when the mass of the rocket is continuously reducing on account of fuel burning and converting into exhaust gases? Let us work around this and see how we get two important equations that help us understand the thrust and the velocity change a rocket experiences as the mass of the rocket changes due to burning of fuel and its conversion to exhaust gases. Let us say you have a rocket and at time t its velocity is v and its mass is m. And the velocity of the rocket is assumed to be that as observed by you from the earth, or in a more scholarly way, we say the same thing as velocity v is measured with earth as the inertial frame. Then after time delta t or at time t plus delta t, let's say the situation is like this. Its velocity has increased to v plus delta v, but its mass has reduced by delta m because it's got converted into exhaust gases, and therefore the exhaust gases would have a mass delta m. Let's assume the velocity of these exhaust gases is u relative to the rocket. Well, if the law of conservation of linear momentum is to hold, assuming it's in outer space and there are no external forces acting on the system, we can say that the momentum before should equal the momentum after time delta t. Let us say the momentum at time t is nothing but mv, and this should equal the momentum of the rocket at time t plus delta t, which is m minus delta m into its velocity, which is v plus delta v. And now we will add this momentum to the momentum of the exhaust gases as well. And why do we add this? Simply because this is our system. But before we do that, you must remember that u is the relative velocity of the exhaust gases, that is relative to the rocket. But we've assumed the velocity v of the rocket is to an observer on Earth. So the velocity of the exhaust gases to an observer on Earth would be v minus u. And I know this part confuses a lot of students. So I've put the derivation and explanation of v minus u in the description below. But intuitively also you can imagine that since the exhaust gases are moving down and the rocket is moving up with velocity v, to your eyes velocity of the gases would have been v if it was moving up along with the rocket. But since that is not the case, and on the contrary it is in the reverse direction, you got to subtract that from v to get the exhaust velocity relative to you as an observer on Earth as v minus u. So the momentum of the exhaust gases would be delta m into v minus u. So let's go ahead and simplify this equation, and what we have is on the left side mv and the right side is mv plus m delta v minus delta mv minus delta m delta v plus delta m into v minus delta m times u. And we can see that many terms cancel out, that is mv cancels with mv, then these two guys cancel out, and delta m delta v being very small can be ignored. So this simplifies to m delta v is equal to u delta m. And this is an important equation where if we divide both sides by delta t, we get m delta v upon delta t is equal to u delta m upon delta t. Now let us take delta v, delta t and delta m to be infinitesimally small. That means the change is happening in an immeasurably short period of time, which basically implies nothing but the fact that we are looking at the situation at some instant of time. So we get m dv upon dt is equal to u dm upon dt. Now, taking dv upon dt as a rocket's acceleration, the equation simplifies to ma is equal to u dm upon dt. That can also be written as df is equal to u dm upon dt. And we say that dm upon dt is simply the rate at which gases are being emitted, and label it as r. And then we have df is equal to u times r. So this is our first rocket equation, which says that the mass into acceleration of the rocket, which we also call the thrust that the rocket experiences, is proportional to the relative speed u of the ejected fuel and to the mass of fuel ejected per unit time. So you see, if the two are constant, the thrust on the rocket will continue to be constant. However, an interesting observation to make is that while the thrust is constant, the acceleration of the rocket keeps increasing. And this may sound a little surprising at first, but then you have to remember that when you write this equation in this form, you realize that while this part is constant, m is constantly reducing as the fuel is getting burned, and therefore the value of A keeps increasing. So this equation tells us that if you want to have a powerful rocket, it should burn fuel at a rapid rate, that is large dm upon dt value, and eject the exhaust gases at a high relative speed u. So when rocket propulsion was a relatively new science, people who were not aware of the idea of conservation of momentum thought that a rocket would not be able to function in outer space because there is nothing to push against. But rockets work really well in outer space because of absence of air resistance. So remember, the rocket here is not pushing against the ground to rise up into the air. Okay, for our next rocket equation, we go back to this equation, that is m dv is equal to u dm, and rearrange it as dv is equal to u into 1 upon m times minus dm. Now the question you would have in mind is, why have we taken minus dm here? Well, the answer to this is that if the mass of the rocket at time t was m, and the mass of the rocket at time t plus delta t is m minus dm, then m t plus delta t minus mt is equal to m minus dm minus m, which equals minus dm. That is, this accurately reflects the decrease in the rocket's mass over time, and this negative sign ensures that the physical reality of reduction of mass due to burning of fuel and exhaust gas expulsion is correctly represented in this equation. So we go ahead and integrate by applying limits for velocity changing from v0, that is the velocity when the mass of the rocket is say m0, that you can call the initial condition, to v when mass reduces to m at a later time. And when we do so, we get v minus v0 is equal to minus u ln, or the natural logarithm of m upon m0, or v minus v0 is equal to u times ln of m0 upon m. And this relationship is known as the second rocket equation, or Tsiolkovsky's rocket equation. Now you should be very clear about each of the terms in this equation. So let us run past each once more. V here is the velocity at some time t when the mass becomes m, that is the rocket has burnt off some fuel. v0 is the velocity at some initial time when the mass is m0, and u is the velocity of the exhaust gases relative to the rocket. Therefore, this ratio of original mass divided by the mass at any given time after the fuel has been exhausted is of great importance to engineers, and they try to make it as large as possible, because more the value of this ratio, higher this quantity or larger the right hand side and more the velocity gain. So I suggest you should go through this playlist, which has a lot of other topics around center of mass, collision and linear momentum. And if you like this lesson, do give it a thumbs up and I will see you in the next lesson.